Today we are working on lesson 5.5. So we are going to be using all of the strategies that we've been learning about for the past week and using different problems to use those strategies. So we're going to be using equivalent ratios. We might use a table or double number lines or that proportion strategy that we've been working on. So there's lots of ways to solve these problems. So you can decide which way works for you. So let's go ahead and look at task 1 here. So task 1 tells us that lemons are sold in bags of 6 for $4. So we get 6 lemons for $4. If you bought 24 lemons, how much would you spend? So I know I've got lemons and I've also got money. And I get 6 lemons for $4. And I'm looking to buy 24 lemons. So I'm going to line up 24 on the top with the lemons. And I'm looking for how much money that would be. So these numbers are nice factors of each other. So I can ask myself, how did I get from 6 to 24? Well, that's times by 4. And now we need to do the same thing on the bottom to make it equivalent. So 4 times 4 is 16. So if I wanted 24 lemons, I would spend $16. So now we also need to know the unit rate. So our unit rate is we have our lemons, and I want to know if I have 6 lemons and they cost $4, if I bought 1 lemon, how much money would that be? So here I'm doing 1 times 4 is 4. And then I'm saying that 6, so now I need to divide by 6. So we have $4. And we need to divide by 6 to see how much 1 lemon is. So remember, this word unit means that I want to know how much 1 costs. So go ahead and see if you can finish this problem here to see what is the unit rate. So 6 cannot go into 4, but it can go into 40 6 times. 6 times 6 is 36. And then there's 4 left over. Bring down my 0, it goes in there 6 times. That's going to keep on going forever, 0.666 forever. So each lemon is about 66 cents for each lemon. So one thing I noticed is that when I set this up, I had my lemons on the top, my money on the bottom, and 6 was bigger than 4, and 1 is bigger than 0.66. So that ratio stayed the same with the bigger number on top. We could have also, so let's take a look here and see what would happen if we set it up the other way. So let's put money on the top and lemons on the bottom. So I spent $4 and got 6 lemons. And I want to know how much money I would get or how much money I would spend if I bought 1 lemon. So I do the same thing here. 1 times 4 is 4, and then we'd be dividing by 6. It equals 0.66. So as long as your numbers going across are matches, it doesn't matter which way you set it up, you'll get the same problem. As long as you have the same, so I had my money on the top, lemons on the bottom, or up here I had all my lemons on the top. So as long as your items going across are the same, you'll end up doing the same problem. So now let's look at this problem using a couple different strategies as well. So we've already solved it one way, so let's try another. So we could use a table, and we could say that every time I have a bag of lemons, I get 6 lemons, and it costs $4. So if I bought 2 bags of lemons, it would cost $12. So we times by 2 times by 2. So we need to times by 2. So now how did I get from 4 to 12? Well, that's times by 3. So I need to do 6 times 3 and 1 times 3. And then I can look here, how did I get from 6 to 24? Well, that's times by 4. So I need to times by 4, times by 4. So one thing to notice is we always came back to this basic one here, the very first one, and did everything from there. So, and then this strategy is just the one we used before. We had 6 lemons that cost $4. We had lemons on the top, money on the bottom. I like to put the labels just to help me remember. And then I know I wanted 24 lemons matched up. So how did I get from 6 to 24? Well, that was times by 4. So I do the same thing to the top and the bottom. We times by 4 on both of these. Okay, so we're going to go ahead and complete task 1 now that we've looked at that problem a few different ways. So first here, we're just writing our ratio of lemons to money from our problem. And we need to figure out the cost of one of these lemons. So we want to find that unit rate. So actually, what is sorry, I did not read that problem very well. What is the unknown value you are looking for in the problem? So we're looking for, if I bought 24 lemons, how much money we would spend. Let's go ahead and fill out the chart and tell me how much the problem ended up being. So then here's that second way. This is my favorite way, is the proportion strategy, is setting these up, because then no matter what I was looking for, we could find that by matching everything up. And then our turn and talk asks us how we could use the relationship of 6 lemons to find the relationship between 24 lemons. So how did we use $6 lemons for $4 to make 24 lemons and $16? So tell me about how those are the same there. So go ahead and pause and finish up task 1, and then come back when you're ready to do task 2. So task 2 is about some slime here. And Jara is making a batch of slime, and our diagram here, so our tape diagram, shows the ratio of hot water. So I have 1, 2, 3, 4, 5, 6 parts of hot water to cold water, which is 1, 2, 3. So I know I need 6 hot waters and I need 3 cold waters. That means I also need to find the total amount of water. So when I have 6 parts hot and 3 parts cold, 6 plus 3 is 9. So he wants to use 18 parts of water total. How many parts of cold water does he need to make the slime? So I'm comparing my total and my cold water. So I'm going to set up a proportion, and I'm going to put total on the top and cold water on the bottom. Now we could switch these as long as we match everything up. But since it asked for total first, I'm going to put my total on the top, cold water on the bottom. So I know when so I'm just going to say what I know. I know when there's 9 parts of water that I need 3. So we just always start with, what do we know? And I'm trying to find 18 total. So I'm going to match up 18 on my total section. And then I'm looking for the cold. So I can ask myself, how did I get from 9 to 18? And that is a nice number. Those work out perfect. So I can say, well, I times by 2. And I times by 2 here will tell me how much cold water. So I want to look at, if the numbers were not nice, what we would do, and if we would come up with the same answer here. So I know I'm looking for 18, or how much cold when I have 18. So let's say that I don't know how many times 9 goes into 18. So I can rearrange my problem and do 3 times 18. So 18 times 3, so you just take those diagonal numbers and multiply. 3 times 8 is 24. 3, 4, 5. So I have 54. And now we're going to divide by 9. And 9 goes into 54. That was a bad 4 with my mouse there. It goes in there 6 times. So I would need 6 cups of cold water. If I double check up here, 3 times 2 was 6. So I got the same answer. This one is a little easier just because 9 is a factor of 18. But sometimes we will be working with numbers that are not nice factors and they're not fact families of each other. So they won't always go in there perfectly. And that's when this proportion strategy really comes in handy. So let's answer a few other questions about this. So we know we have 6 hot, 3 cold, 9 total. So if Jera wanted to make a larger batch of slime using 36 total, so it's really important that we're paying attention to what these numbers are asking for. So 9 is our total. So we know we're looking for a total. And how many parts of cold would they need? So I'm comparing total to cold. So my total is 9. My cold is 3. So that's what I know from the problem. Now I'm looking for 36 total. So I'm going to match up 36 here. And I'm looking for the cold. So we can do 36 times 3 and divide it by 9 will tell us how many cold cups of water we need. So G asks us how many parts of hot water, so I know I'm looking for hot, will he need if he uses a total of 18 parts? So I'm comparing hot to the total now. So different type of problem than total and cold. So hot water is 6, total is 9. And we want to know how much total or how much hot water we need when we have a total of 18. So I notice these are nice factor numbers. So I can say that 9 goes into 18 2 times and do the same thing to the top. And that will tell me how much hot water I need. If I don't notice that 9 is a factor of 18, I can times 6 and 18 and then divide by 9 as well. And either way, you're going to get the same problem or the same answer. And another problem it asks us is how many parts of hot water, so we're comparing hot, will he need if he uses 36 total? So now I'm comparing hot to the total. So hot water is 6, total is 9. So it's just really important that we read what are we comparing. And now I want 36 total. So 36 total is matching up with the total. And I'm looking for the hot. So I notice 9 goes into 36 an even amount of times. And you're going to do the same thing to the top to make these equivalent ratios. Okay, so using these setups, we're going to go ahead and complete task 2. So we need to know the total parts of water, and then we're matching up total to cold, just like we did. And then you're telling me what you notice about that relationship there. And then it wants to know cold water to 18. Now we want total water to cold water for 36 total. Then it's that hot water to total water for 18. So these are all problems we did. So you can go back and look at your work and you should have these answers already. And then we have the hot water to total 36. So then tell me, how could you use your tape diagram to check your answers? So how would the answers you got from these proportion problems match up here? So let's go back here. So we know that this was 6. So I know if I needed 18, we times everything by 2. So if I put 2 in each of these, 2, 2, 2, 2, 4, 6, my answer was 6. So whatever we multiplied by, if we put that number here in each box, it should add up to our answer. So I said I needed 2 of everything, and 3 times 2 is 6, 2, 4, 6. So explain to me how we could use our tape diagram to check all of our proportions there. So when you are done with task 2, go ahead and come back and let's do task 3. Okay, task 3 tells us that a race car driver completes 5 laps of a race in 3 minutes. So we know we have laps to minutes. So 5 laps takes him 3 minutes. Oh, and so I didn't keep reading. And 30 seconds. I know that it takes 60 seconds to equal 1 minute. So if I have 30 out of 60, that equals a half. And as a decimal, that's 0.5. So when we're using fractions, I don't want to give another fraction in my fraction, but we can put decimals in our fractions. So the driver continues at this rate. So it's a constant rate, 5 laps every 3.5 minutes. How many laps will the driver complete? So I'm looking for the laps. So I know I'm looking for laps. Will the driver complete in 17.5 minutes? So 17.5 should match up to my minutes row. So I do not know how many times 3.5 goes into 17.5. But I can rewrite this problem to get L by itself. And I can take this, and the opposite of divide is to times this. So I can do 17.5, and I can multiply that by 5. And then we're dividing it by 3.5. So I'll need to move my decimal and move my decimal in the answer. So I want you to go ahead and try that and then come back and see if we get the same answer. So 5 times 5 is 25. There's 5 times 7 is 35, 36, 37. 5, 6, 7, 8, and 1 decimal place. So I know I need to divide by 35, so I need to move this over 1 as well. So we have 875, and we're dividing by 35. So if you've not already done this, make sure you pause and do that. So I promise you practicing this work is going to help you instead of just watching me do it. So 35, I know can't go into 8. And 35 doubled, I know, is 70. 30 more is 100, and 5 more is 105. So let's start there and see what we can get to. So I know it can go in here 2 times is 70. And then I'm subtracting. I have 175 left. So I know 30, actually I'm going to add my 5 more is 110, and 30 more is 140. 30 more is 170, and 5 more is 175. So 1, 2, 3, 4, exactly 5 times. So to do 25 laps, it will take 17.5 minutes. So another thing we should ask ourselves is, what is our unit rate? So I want to find out how many laps they can do every minute. So I want to know how many laps per minute. So I know it's 5 laps in 3.5 minutes. And I want to know how many laps they can do in 1 minute here. So to get from 3.5 to 1, I would divide by 3.5. So I do the same thing up here, 5 divided by 3.5. So I have 3.5, and I know I need to move my decimal over. which the decimal on the 5 is at the end. So I need to add a decimal place. So I'm really doing 35 into 50. Goes in there one time. 1 times 35 is 35. And subtracting is, let's make sure I did that right, is 15. And I'm bringing down a 0. And up here, I have my 35s already counted. 1, 2, 3 goes in there 4 times. And 4 times 35 is 140. Then we've got 10 left over, and it goes in there 2 times. So I know every minute they're doing about a lap and a half. We can also do this the other way, and let's see if that's maybe a little bit of a nicer number. So I want to know how many minutes per lap. So I know it's 5 to 3.5. And now I want to know how many minutes it takes per 1 lap. So we just flip this here. So I know every minute they can do about a lap and a half. So let's just see if this gives us a nicer number, because this one is going to keep on going here. So we know to get from 5 to 1, I would divide by 5. So if I take 3.5 and divide by 5, I think this will be a nicer number for us to work with. So I know 5 can't go into 3, but it can go into 35.7 times exactly. So to do a lap takes 7/10 of a minute. So more than half of a minute. So we want to fill out this chart using our unit rate. So I know they can do 5 laps in 3.5 minutes. Now, looking here, I know that I times this by 2. So we're going to times 5 by 2. So now they added another group of 3.5. So this is times by 1, 2, 3. So now we're going to times by 3. 5 times 3 is 15. How did I get from 5 to 20? Well, I times by 4. So now I'm going to do 3.5 times by 4. So each time I'm just going back and forth. How did I get from here to here? And then we do the same thing to the other side to keep them equivalent. So let's go ahead and complete task 3 here. So our ratio of laps to minutes, so we know we have 5 laps to 3.5 minutes. Then see if you can fill out this number line doing the same thing to the top and the bottom each time there. And then tell me how that, complete the double number line and tell us how each pairs are equivalent. So how do you know that every time we moved over that they were equal to 5 and 3.5? And another way to find an unknown quantity is to find a factor that generates the equivalent ratio. So what number multiplied by 3.5 will result in 17.5? So if we come up here, we should be able to figure out, how did I get from 3.5 to 17.5? How many times did we have to multiply that? And then this is our proportion strategy. We know we had 5 to 3.5. We're doing the same thing to the top and the bottom here. And then how many laps did they do? Hey, if you have any questions, so go ahead and fill out task 3. Then if you have any questions or anything I can help you with, please let me know.